All right. In this video, I'll be talking about the generalization to the Riemann integral, okay? And what is the Steiltjes integral, right? So that's mainly what we're going to be diving into today. So pretty much it might sound a little intimidating at first, but I'm pretty sure by the end of this lesson, of course, you're going to understand how it works and pretty much it'll extend what you already know about integration. So let's pretty much start off with the most basic integral that we all know and are familiar with, right? So pretty much the Riemann integral, where we have to write it as the integral from a to b of f of x dx, right? And we're essentially adding up the values of the function f, right? Multiplied by tiny changes in x, which is our dx, right? So we just basically think of it as adding up all the little pieces of f of x as x moves from a to b, right? And this is mainly shown by using rectangles, right? So let's say we have a curve right right here, right, from A to B, right? And pretty much what the Riemann integral does is pretty much it makes infinitely small rectangles, right? And pretty much these infinitely small rectangles with a very small width, they gave you the area of the function, right? Pretty much under the curve. So that's pretty much how we view Riemann integrals. And here, what we're going to do, right, is pretty much now we're going to pretty much introduce the idea behind the Steiltjes integral. So, like, what if instead of integrating with respect to x, right, instead of dx, we integrate it with respect to another function, which is pretty much what the Steiltjes integral is, right? Which pretty much we would write our Steiltjes integral as the integral from a to b of f of x d g of x, right? And pretty much here alpha pretty much is called the integrator function, right? So g is the integrator function, okay? And it pretty much works just like dx in the Riemann case, right? But now, like, the increments are pretty much determined by how much g of x changes, not by how much x changes. So the question is, right, why would we do this? Well, like, imagine you're pretty much tracking a moving object, right? Like, let's say instead of regular time intervals, you measure pretty much on another quantity, right? For example, like, I guess we could say fuel consumption, stock prices, population growth, or stuff like that, right? The Steiltjes integral lets us pretty much accumulate values of a function weighted by changes in another function, right? So, like, for example, if like we say that g of x is increasing steadily, it behaves like a normal integral. But if it jumps or stays flat in places or has specific discontinuities of the Steiltjes integral accounts for that. So let's go ahead and look at one example, right, where g of x is a function, mainly a step function, right? So here, let's say g of x is equal to the step function where we have 0 when x is less than some value c and 1 when x is greater than some value c or greater than equal to some value or c. And pretty much when we have our integral, right, let's say f of c is pretty much equal to some function, right? Our main goal is to pretty much say, okay, so our integral, right, a to b of f of x d g of x, right, where we have f of c for values of x, and that determines pretty much how we integrate with respect to our function. So if c is between a and b and 0, right, the integral picks out the value at the jump. So let's go ahead and pretty much look at a straightforward example where we are defining our function f of x. So pretty much we're going to say, right, like, first of all, let's look at f of x. So pretty much we want f of x to be equal to x squared plus 1. And here we want the value of c to be 2. So here we have pretty much our f of x and g of x, right? So pretty much now what we want to do is pretty much compute, let's say, on the interval 0, comma 3. So pretty much for our integral, we're going to have this integral, which is 0 from 0 to 3 of x squared plus 1 and times d g of x, right? So what is happening here, right? How would we integrate with respect to a step function? Well, since g of x, right, is a constant everywhere except g equals 2, right? So let's say g of some value x, right? So let's say c. We're pretty much going to get a constant, right, when where x is not equal to 2, right? So pretty much we have a step function where if we were to graph this, right, we would have something like this. So pretty much it is 0 when x is less than 2. So let's say 2 is right here. And there's a circle because it is less than, and pretty much it is going to be infinitely going to the left. And for 1, right, we see this here, which is going to be a closed circle, and it's going to be going to the right infinitely. So we pretty much see here, right, that there is a jump, right, which is a discontinuity. And pretty much we see that the Steiltjes integral only picks up values where g of x changes. So for this example, right, the entire integral is pretty much going to be like f of 2 times g of 2 from the right side minus g of 2 from the left side. Okay? So the reason we're doing this, right, the reason why it becomes this is because the integral sums up values of f of x, right, or x squared plus 1, multiplied by the jump in g of x at pretty much the exact point x equals 2. Because at x equals 2, the jump occurs. So now what we want to do is pretty much compute it, right? So we have f of 2 is simply going to be 2 squared plus 1, which is going to be 5, right? And now we want to find what the jump is, right? So we pretty much have the jump at g of x is going to be g of 2 from the right side minus g of 2 from the left side. This is going to be 1 because if we look at the right side of g, it is going to be 1. And 2 from the left side is going to be 0, so minus 0. And it's going to be times 1, where f of 2 is equal to 5. So pretty much that tells us that this integral right here becomes 5, right? So even though limits are from 0 to 3, right, the only thing that matters is what happens at the jump at x equals 2. And pretty much that's pretty much the whole point of integrating with respect to another function, mainly a step function, right? So let's just clear this up really quick. So pretty much now that we looked at one example, right, we could now formally define the Steiltjes integral like this, right, where we take a partition from our interval a to b, and we say a is pretty much equal to x1, which is less than x2, and so on, and then which is less than xn, which is equal to b, right? So all these partitions pretty much could become a sum, where we say that pretty much we have our sum for our Steiltjes integral from I equals 1 to n, and we have our function f of ti and times g, of xi, and then that is subtracted by g of xi minus 1, right? Where ti is pretty much some point in this interval right here, xi minus 1, comma, xi, right? So t is between the interval xi minus 1, comma, xi, right? And pretty much as the partition gets finer and finer, this sum approaches a Steiltjes integral, right? So that's basically the formal definition of the Steiltjes integral. And for special cases, right, we're going to look at g of x where it is equal to c, right? This pretty much, this Steiltjes integral is just our regular Riemann integral, which is the integral from a to b f of x dx. And pretty much here, right, we look at g of x as and that just becomes our Riemann integral, which then if we were to say g of x is equal to the step function as we saw earlier, the Steiltjes integral becomes a weighted sum. And if g, right, is continuous, so if g is continuous, right, and differentiable, then we can write our, well, yeah, I forgot to mention, and if g of x is existing, you can pretty much write our Steiltjes integral, right, from a to b f of x d g of x. We could pretty much write this as the integral from a to b of f of x g prime of x dx. So pretty much it just generalizes back to the Riemann integral with a weight function. So let's go ahead and look at an example where we have g as a continuous function, right? So we're going to have the integral from 0 to 1 of x plus 2, and we're going to integrate with respect to x squared plus 1. So first, let's go ahead and look at our d of x squared plus 1. How would we integrate this, right? Well, we know that x squared plus 1 is continuous because it pretty much has values existing everywhere. There's no jumps, no discontinuities, asymptotes, or anything. So what we can do, right, is pretty much look at g of x, right, and we have x squared plus 1. And differentiating, right, g prime of x, we get that is 2x dx, right? So since we now have this g of x, we'll just remove the dx, we could pretty much rewrite our integral as the integral from 0 to 1 of x plus 2 times 2x dx. And just multiplying what we have inside, we see that we have just a basic Riemann integral, which we can go ahead and evaluate. So multiplying 2x by x, we get 2x squared, and 2 times 2 is 4, so we got 4x and dx. And then here we would have x cubed 2 over 3, and then plus 2x squared evaluated from 1 to 0, which is just going to be 2 over 3 plus 2, which is going to be 8 over 3. So we have this is 8 over 3, meaning that our original Steiltjes integral is 8 over 3. So let's go ahead and look at another example, right? So let's say we have an integral from 0 to 2 of square root of x times d root x. Here we are differentiating the square root of x with respect to square root of x. So here what we can do, right, since we know that g is continuous, we could say that g prime of x is equal to 1 over 2 root x. And pretty much if we just write this as a Riemann integral, we would have the integral from 0 to 2 of the square root of x times 1 over 2 root x dx, and the square roots cancel out. Pretty much now we could rewrite this as the integral from 0 to 2 of 1 half dx, which then pretty much just would just become 1 half x evaluated from 2 to 0, which we know that 1 half times 2 is just going to be 1. And then after that, we subtract 0, and that gives 1. So pretty much our original integral is 1. And that is pretty much what is the Steiltjes integral for a function when you're pretty much integrating with respect to itself. So it pretty much works out very neatly. So those were some few examples that were pretty much worked out. And yeah, it was fairly straightforward. And now what about the applications, right? Like the Steiltjes integral was pretty much very useful in probability, right? Where we integrate with respect to a cumulative distribution function or a CDF, which is pretty much important in Fourier analysis, measure theory, and spectral theory. And of course, it's pretty much going to always be able to help you with a lot of things in probability mainly, as that is the whole purpose of the Steiltjes integral. So yeah, pretty much the Steiltjes integral, right? The integral f of x with respect to g of x pretty much lets us integrate a function not just with respect to regular changes in x, but with respect to the changes in another function. It's a pretty flexible and powerful tool that generalizes integration in many ways that could connect probability analysis, measure theory, gambling, and a lot of other concepts. So yeah, pretty much that's it, and hopefully this helped you understand the Steiltjes integral. So yeah, thank you for watching and have a good day.